have your formula sheets handy. You can pull those out. Just like everything else, we've got a lot of formulas on here, so pretty much every formula I'm going to give you is also on this formula sheet. We really are just learning how to use them, okay? So first we have a couple little definitions. If I'm talking about probability, you should know what that means. So probability is just the likelihood of an event occurring. So if I say the probability is 75%, there's a 75% chance of rain. That's a probability.
Is that always a percent?
So it's a number between 0 and 1, which can be translated into a percent. You'll never have a negative, you'll never have a probability bigger than 1. It's always between that 0 and 1. So next thing we have the law of large numbers. It says as the number of trials increases, the closer the probability gets to the expected probability. We're going to talk about the difference between like an expected probability and what you actually see. If I flip a coin, what's the probability of getting a heads?
50%.
50%. Does that mean if I flip the coin twice, I get one head and one tail? No. Is it possible that I could flip the coin 10 times and get heads every single time?
Yes.
Yes. But what this says, as the number of trials increases, it should get closer to what I expect with 50%. So maybe if I flip it 10 times, I only get one tails in that. But if I were to flip it 100 times, would it be closer to 50-50? Yes. If I flip it 1,000 times, is it probably going to be even closer? Yes. So just because there's a 50% chance of getting heads doesn't mean in 2 flips that's what will happen. But as time goes on and we do this experiment over and over and over again, it will start to get closer to that number. Okay, so a few other terms that we're going to be using. We'll talk about a sample space. We use the capital S to denote that. And that is just a collection of all possible outcomes. So if I am flipping a coin, what would my sample space be? Yeah, heads or tails. If I am flipping my coin 2 times, what would my sample space be? We could have heads and then a heads, a tails and then a tails. I could have heads and then tails, or tails and then heads. So your sample space is everything that could happen, every possible outcome. An event is just a collection of outcomes. So if I flipped my coin 3 times and I got tails, tails, heads, that's an event. That's what I saw happen. I want to look at probability experiment of having 2 children. So part A, identify the outcomes. What are your options if you have a child? You can have a boy or you can have a girl. We're just going to use PG, make things easy. So the sample space is a list of every possible outcome. If we have 2 children, we could have boy, boy, we could have boy, girl, we could have girl, boy, or girl, girl. That's my sample space. Which ones would be the event having 1 boy?
PG and GB.
So that's just kind of getting us used to those terms. An outcome is what could happen. Sample space is the list of every possible outcome. An event is one scenario that meets that requirement. So far, so good? So a couple of things about probability that, one of them we've already touched on. Probability is like a percent, so it has to be between 0 and 1. If you add up all of your possible probabilities, what should it add up to? So those are the two probability rules. Every probability has to be between 0 and 1, and the sum of all the probabilities has to equal 1. One of the big things that we're going to be doing, starting in this section but moving forward, we're going to be making probability models, which essentially lists every outcome and the probability of that outcome. So when we make our probability models, a couple things to keep in mind. If something is impossible, what do you think the probability is?
0.
Okay, if it is certain, what would be the probability?
1.
Okay. So, last few definitions. I know we've had several on here. So your probability model just lists all the outcomes and their probability. Impossible means probability is 0. Certain means the probability of 1. One other thing that we will use a lot is an unusual event. And unusual doesn't mean impossible. It can happen, but it means it's not likely to happen. So for us, unusual will be less than 5%. So anytime a probability is less than 5%, we would say that would be an unusual event. So let's say we get a bag of M&Ms, and we know that M&Ms come in different colors, right? So if I get a bag of 100 M&Ms, and in this bag we have 12 brown, 15 yellow, 12 red, 23 orange, 23 blue, and 15 green. I want to make a probability model. So a probability model is really just like a table. We're going to list our outcome, which is color, and then we're going to list the probability. So my different outcomes, we can have brown, yellow, red, orange, blue, and green. Okay, how would I get those probabilities?
Take how many there are divided by 100.
So there are 12 browns divided by the 100 total, so 12 over 100.
0.12.
Yellow, we have 15 out of 100, 0.15. Red, 12 divided by 100 is 0.12. Orange, 23 out of 100. Blue and green, 15 out of 100 is 0.15. Quick check, if it's a probability model, every one of your probabilities has to be a number between 0 and 1, which they are. And what should they add up to?
100.
100. So if you add those up real quick, does it add up to 1? I believe it does. So that's a quick check to make sure we're on the right track. Okay. There are 3 types of probabilities. The first is empirical. So an empirical probability is basically like when we talked about flipping the coin. Okay, what's the probability of getting a heads? 0.5. Is that necessarily what happens if I give you a coin and you flip it 10 times? No, but if we keep doing that, then most likely it will approach that. So empirical probability is kind of like your expected. Okay, so if I said the probability of getting a heads when I flip the coin is 0.5. It's what we expect to happen, what should happen. Classical. Okay, so classical is more like what does happen. Okay, so when we flip our coin, let's say if we did it 12 times, and well, let's just do 10 times, and we got 3 heads. And what was the probability of getting heads in my experiment?
50%. Oh no, 1/3.
Yeah, if we flip 10 times, we got 3 heads, then the probability of heads is 3/10 or 0.3. So classical is what actually happens. Okay. We know if we keep doing this, it should look more like our empirical, what we expect. But if I just ask from our experiment, it's what actually occurred. Okay, the third type is subjective. And subjective is based on personal judgment. Can you think of a probability we hear all the time that's kind of based on personal judgment? Think about the weather. Probability of rain is 10% today. Is that like a hard science where we can, like flipping a coin where there's only 2 outcomes and you can look at that? No. So weather is an excellent example of a subjective probability. Okay, it doesn't mean it's bad, but it's not, 2 people could calculate that probability and have 2 different answers because they're including a little bit of personal opinion in there. Okay, so let's just practice some probabilities for the rest of the day. An insurance agent insures 182 teenage drivers. Last year, 24 of the teenagers had to file a claim on their auto policy. Based on this, what is the probability a teen will file a claim? So what would you do? Your probabilities you can write as fractions in lowest terms or decimals. If you go with a decimal, please give me 4 decimal places. Just a little more precise there. So if I'm going to make my assumption based on this, it is 0.1311. That's the probability of a teenager having a claim. Let's look at this one. Have you guys ever played Pass the Pigs? It's a fun game. You should get it. So it's like 2 little pigs are your dice, and you get different points based on how they land when you roll them. Okay. So I want to use the results of this experiment to build a probability model for the way the pig lands. So here are the different outcomes. There's their frequency. So we had 52 students playing this. How would I get my probability model? What would I have to do here? We need to add them all up. So then we really are just going to add probability to this table. You could rewrite the table, obviously, if you're doing it on your own. You don't necessarily have to have all 3 columns for the probability table. You need the outcome and then the probability that happened. So to get each probability, you divide by your total. So the probability of landing on a side with no dot is 0.3412. And if I asked you if this was a probability model, what would you have to check? Every probability has to be between 0 and 1, and it has to add to 1. Now, is there a possibility that this won't add up to be exactly 1?
Yes.
Yes, why?
Because of the rounding.
Rounding error. We rounded all these to 4 decimal places, but it should be very, very close. So far, so good. So part B, estimate the probability that a thrown pig lands on a side with a dot. Would it be unusual to throw a leaning jowler?
Yes.
What's the probability of a leaning jowler?
0.081%.
Right, so that's 0.81%. We said if it's less than 5%, that would be unusual. So this would definitely be an unusual one. All right. So far, so good? Okay, so both of these probabilities that we just got done doing, these are empirical. They're kind of are expected, they are based off the data that we had, the real life data. So when you just take the number of times it happens out of the total number of occurrences, that is your empirical probability. So an example of a classical probability. Let's say we've got this bag of M&Ms. We have 9 brown, 6 yellow, blah, 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 blah. If I want the probability of getting a yellow. Okay, so how many total pieces of candy are in my bag? $30. So the probability of getting a yellow out of that would be
0.2.
you do 6 yellows out of the 30 total pieces, and you get your 0.2. Okay, each piece, the key to classical, every outcome is equally likely. When I pick a piece of candy out of that bag, am I more likely to pick up one than another? No, they all have an equal chance of being selected. That's what makes this classical. The probability that it is blue. So how many blues do we have? 2. Out of the 30 total, and we get All right. So what could you say about the probability of a yellow versus blue? Yellow is more likely, which we would expect, wouldn't we? There's more pieces of yellow in that bag, so that's not a surprise. It has a higher probability. Just a couple more examples. Sophia has 3 tickets to a concert, but Yolanda, Michael, Kevin, and Marissa all want to go with her. To be fair, Sophia randomly selects 2 people who can go with her, so determine the sample space. Why don't you guys try this on your own? On the sample space, so you're listing the people, you can just use like Y, what should we call it? Michael, M-I, Kevin, K, Marissa, let's do M-A. So list your possible outcomes. So you can have Yolanda and Michael, Yolanda and Kevin, Yolanda and Marissa, Michael and Kevin, bless you, Michael and Marissa, Kevin and Marissa. So we have 1, 2, 3, 4, 5, 6 different possible outcomes. So what's the probability that Michael and Kevin get to go?
1 out of 6.
The nice thing about sample space, it kind of helps you determine these probabilities. Determine the probability that Marissa attends. So Marissa, she's here, here, and here. So 3 out of the 6 total ones have Marissa. 0.5. Interpret the probability in part C. So what this means is there is a 50% chance Marissa attends. So interpret is just writing a sentence, changing your probability to a percent. Last example. A survey asked 500 families with 3 children the gender of their children. It was found that 180 families had 2 boys and 1 girl. So part A, estimate the probability of having 2 boys and 1 girl using the empirical method. So if I'm looking at this, how many families had that?
180.
Out of how many total families?
100.
So if we divide those, that is 0.6.
0.36.
Oh, yeah, I typed in 300 instead of 500. Sorry about that. I was thinking that does not seem right, that it's more than 50% likely to have 2 boys and 1 girl. Okay, here we go. Let's do this using the classical method. So empirical is looking at our data and just finding that probability. Classical would be like listing out our sample space and calculating our probability from there. One way we've done the sample space, another option you might see sometimes is what's called a tree diagram. So I'm not going to care how you get it, but I'm going to show you a tree diagram just so you've seen it before. So when you have a child, your options are boy or girl, right? That's our first child. Then for the second child, if you had a boy first, your second one could be a boy or a girl. If you had a girl first, your second one could be a boy or a girl. And we have a third child, so what do I need to do? You know, you're going to add another branch for each of these options. Okay. So, when I look at this, how many options are in my final branch? 1, 2, 3, 4, So my total is out of 8. I want the ones that have 2 boys and 1 girl. So we could go boy, boy, girl. That would be 1. We could do boy, girl, boy. That's 2. If we start with a girl, we could do girl, boy, boy. And is there any other option that has 2 boys? So that's 3 out of 8, which is what? If you want to do a decimal.
0.375.
Okay. These two are pretty similar. This is kind of the law of large numbers. If I took if I took 1,000 people instead of just 500 in my study, then it would get closer to this 0.375. Okay, any questions for me there?
Where did you get the 8 from?
I looked at my final branch, how many different paths there were. So I just really counted how many outcomes were in that last section. Yes?
So if we're doing the empirical, then we just like look at the actual numbers they gave us, but the classical, we have to like
Look at your outcomes. Look at all the possibilities.
Okay.
All right. So that's all for today. So your assignment. Let's do. Okay, on this, listen carefully, this will save you a lot of time. A lot of these questions say find and interpret the probability. So it's telling you to find it and then write a little sentence about what that means. You do not have to interpret on those questions. So the questions where it says find and interpret, you only have to find it. The only time I'm going to make you actually interpret a probability is like when that's the only thing the question asks for. So there's one, like part A says find the probability and part B says interpret that probability. So if it only asks you to interpret, that's when you write your sentence. If it just says find and interpret, you only have to find it. Does that make sense to everyone?